Hey guys, Miss Miklos here, and in our last lecture we really looked at exponential functions and kind of explored what those look like. And today we're going to be talking more about logarithms. The good news is a lot of what we're going to be talking about today is something you guys have already learned, which is awesome. So we just are going to go ahead and look at this graph. We should be pretty familiar with what this looks like, y equals 2 to the x. We graphed it like a billion times in our last lecture. So using this table or the graph, we can see that 16 is the same thing as 2 to the 4th power. So the question we really want to explore here is, can any number be written as a power of 2? For example, what power of 2 is 60? So in order to find this, we can graph, and let me kind of zoom in and write this in, we can go ahead and graph y equals 2 to the x and y equals 60 and find the point of intersection. And what we would see is that the power of 2, that is 16, is 4, and the power of 2, that is 60, is approximately 5.907. So in fact, in your calculator, if you did 2 to the 5.907 power, we would not get 60 exactly because this is a rounded value, but we would see it gets pretty close. So what this is telling us, and this is kind of the key thing, we talked about logarithms last class that had a base of 10 or a base of e, which was our natural logarithm. And today we're going to be exploring logarithms that have different things. So this is saying log base 2 of 16 is 4. So the correlation I really want us to make today is this is what we call logarithmic form, and this is what we call exponential form. And probably the question I get the most often is, what is a logarithm? And the key thing here is that a logarithm is just an exponent. We call this a base, and if we look in exponential form, it still is a base. So it's 2 to our exponent, so 2 to the 4th equals 16. So in this case, if I have log base 2 of 60 equals 5.907, I know 2 is my base. Our logarithm is equal to the exponent, so 5.907 is our exponent, and that is equal to 60. So we have logarithmic form and exponential form. Now the reason why we need to have logarithmic form, exponential form is great, but I don't really know how to solve this if we have a variable as our exponent. So that's when logarithmic form comes in handy. So for our first set of problems, all it's asking us to do is express an exponential form. So we are taking this logarithmic equation and we are writing it as an exponential equation. So first of all, looking at this, just a reminder, the way we read this is log base 3 of 81 is 4. So notice my base here is 3, so that becomes my base when I go ahead and write it in exponential form. Our logarithm, we know, is really just an exponent, so that 4 becomes my exponent, and it is equal to 81. So these two equations are equivalent to one another. And this honestly is really a memorization that we just need to know how to change things back and forth. Okay, number 2, log base 5 of 25 equals 2. This time my base is 5. My logarithm is equal to 2, so that is our exponent, and it is equal to 25. Now, some of you guys may be thinking right now, why do we even need to know this? Because can't we just put log in our calculator? And I just want to remind you that at the moment, we only know how to use 2 bases in our calculator, a base of 10 and a base of e. At this point, I don't know how to do log base 5, so that's why it's important we know how to change forms. Number 3 looks a little bit trickier, so I'm just going to rewrite this as log base e of 1 equals 0. So that's just a good reminder to us that ln means log base e. So in this case, my base is e, so I'm going to write that as my base. My exponent is 0, and it is equal to 1. Which this honestly makes sense to us anyways because we know anything to the 0 power is 1. And just to show that it really doesn't matter what symbols we're using, here we have log base delta of theta equals infinity. So this would become delta to the infinity power equals theta. There we go. So it really is memorization and practice making sure we're feeling good on this. The next set of problems want us to do the complete opposite. It's telling us to take it from exponential form into logarithmic form. So if we look at number 5, okay, I'm going to go ahead and write log. And we know our base is whatever the base is of our exponential equation. So log base 2. We know that our exponent is what our logarithm is equal to, so I'm going to leave a little space. Log base 2 of something is equal to 3. And we can see that this 8, we would say log base 2 of 8 is equal to 3. So once again, we're doing the same thing, we're just doing it in the opposite direction. My base is still my base. My exponent is what my logarithm is equal to. Okay, so number 6, this time I'm going to say log base 10. We can see that our exponent is -3, so that's what it is equal to. And it's log base 10 of 1 over 1,000 equals -3. Now, this one actually has an alternate correct answer as well. We know log base 10 is our common logarithm. So that means that I could also just write this as log of 1 over 1,000 equals -3. The only time I can leave this base blank is when it is our common logarithm. I also want to stress that this is a logarithmic function. So this is all connected. It's one thing. We can't divide or do something weird like that to get rid of part of that function. Okay, for number 7, this would be log base e, and all of a sudden, a little bell should be going off in our heads because we know log base e means ln. So I have ln of 20.0855 is equal to 3. And we do always change log base e to be ln. So now that we've explored a little bit about the correlation and relationship between logarithms and exponential form, I want to go through these 4 quick properties of logarithms, which actually are really self-explanatory. So this first one, log base a just means any base. It doesn't matter. Log base a of 1 is always equal to 0 because if we change this into exponential form, a to the 0 power equals 1. Our next one, log base a of a equals 1. So what this is telling us is that whenever these two numbers are the same, it's always equal to 1. And the reason is because if we change this into exponential form, a to the first power equals a. Next, if these numbers are the same and I have an exponent, this logarithm is always equal to the exponent because if I change it to exponential form, a to the x power equals a to the x. Lastly, if we have two logarithms equal to each other and they have the same base, whatever we're taking the logarithm of is also equal to each other. Okay, so these problems, we're going to be applying what we just learned with changing things back and forth, and it's telling us to evaluate without a calculator. And even if we had a calculator, that wouldn't help us much because we only know how to deal with a base of 10 or a base of e. So we need to figure out what is log base 2 of 64 equal to. So I'm going to start by saying it is equal to x because that is an unknown value. And that should be the first thing that we're doing, okay, because we don't know what that is. Since I don't know how to solve this using a logarithm, I'm going to change it into exponential form. So that would become 2 to the x power equals 64. And now my goal, I need to get the same base because I know if I can rewrite both of these as a number to a power, if those numbers, those bases are the same, then I know that their exponents are also the same. So I need to think here. I'm going to keep 2 by itself because I can't write 2 as anything else. And I need to think, how can I write 64 as 2 to a power? The reason why I'm choosing 2 is because that's what this base already is. So I would mess around on my calculator. I might see, okay, what's 2 to the 4th? What's 2 to the 5th? And I would eventually figure out that 2 to the 6th power is 64. So in this case, I could say x equals 6. You guys could also write log base 2 of 64 equals 6. Either of those two answers is perfect. Now, some of you might jump from this step to knowing that it's 6, and that's great, okay? But I like writing it out just because we're going to encounter some that are a little bit more difficult. Like number 9. Okay, I don't know about you guys, but fractions can be a little scary. I don't know how to deal with that, so I'm going to change this into exponential form. Now, I may not remember how to deal with a fraction. So I know I need to get the same base still, and I know 81 is the same thing as 3 to the 4th power. So I'm going to write this as 1 over 3 to the 4th power. Now, the issue I have here is I do not have the same number to a base yet. I need to figure out, how can I write this as 3 to the x equals 3 to something? And you guys may remember, we've worked backwards in previous courses. If we had something like x to the negative 2nd power, that was equal to 1 over x squared. And it was really ingrained in our minds, never have negative exponents. They're bad. We want them to be positive. So we're really used to taking this negative exponent and making it into a fraction. Well, today, we're going to work the other way, where sometimes if I have something as a fraction, if I want to bring this value up to the numerator, it makes my exponent negative. So going back to this particular problem, I have 3 to the 4th in my denominator. If I want to bring that up to the numerator, it's going to become 3 to the negative 4th. So I get x is equal to negative 4. Now, if you really want to check in your calculator, you could do 3 to the negative 4th power. And when you convert that decimal value, you should get 1 over 81. Now looking at number 10, if we were allowed to use our calculator, this would be a glorious problem because we know log base 10 is just log. That's our common logarithm. But we're rule followers, so we're going to stick to the rules here and change this into exponential form. So I get 10 to the x power equals 1,000. I'm going to see how can I write 1,000 in terms of 10 to a power, and that is 10 cubed. So I get x is equal to 3. For number 11, if you guys were paying attention earlier, I could say right away that this is equal to 0 because we learned in our 4 properties, if I've log base anything of 1, it is equal to 0. Now let's say I forgot this. Okay, if I was doing this the long way, I would go ahead and write e to the x power equals 1. And this is when it becomes a little bit tougher. Okay, I need to think, well, how could I write 1 as e to a power? And I know anything to the 0 power is 1, so I get x equals 0. I think it's much easier if I would just remember this off the top of my head, or I think it's easier to go from here straight into knowing that our exponent has to be 0 because that's the only exponent that gives us 1 as our solution. Number 12, we have ln. So the first thing that I might do until I get super comfortable with ln is write this as log base e because we know those are the same things. Now, once again, if I paid attention to those properties, I could say right away that x equals 5. Because we said if the base and this number are the same, then my answer is my exponent. Now let's say I completely forgot that if I'm changing this into exponential form, it would become e to the x equals e to the 5th power. And this is actually the easiest one we've had to deal with because my bases are already the same. So I could just say, okay, well then x is equal to 5 and we are done. Last problem, which of course probably means it's the toughest, right? I'm going to have to change this into exponential form. Hopefully we're getting real good at that. And the reason why I think this one gets a little bit tougher is because most of us probably will not think of a way to write 2 as 4 to a power. And kind of a side note here, 4 to the 1/2 power is actually equal to 2 because we know that a fractional exponent is a radical. So some of you may have remembered that, and that's great. I'm assuming most of us don't. So I still need to get the same base. So I see this 2 and I realize, oh, well, I can write 4 as 2 to a power. So this becomes 2 squared to the x power equals 2 to the 1st power. Sorry, I had a visitor there. Back to math. We know when we're taking an exponent to a power, we multiply. So 2 to the 2x power equals 2 to the 1st. So I'm going to take those two exponents and set them equal to each other, and I get that x is equal to 1/2. I just want to point out that that's the same answer I got if I remembered that we could write 2 as 4 to the 1/2 power. So there are multiple ways to get to the right answer here. Key things, we need to get the same base on both sides, and we really need to know how to convert back and forth from logarithmic form into exponential form.